This is a quick video over how to read the triangle diagram. And let's start off with having a component A. And A will be up here. Okay, I'm going to need maybe darker color. A. So at this point, you have pure A. Pure A. And that's what this 100 right here represents. So that's completely pure. What this next line represents right here is actually 90% or 90% A. Then you go down one more, 80, 70, 60, and it goes on like this. And so maybe until you get to the very bottom. Get to the very bottom. Let me see something. Yeah, that's good. Very bottom, right down here, this line represents 0. So that has no A. No A, or 0A as a percentage. And again, so you could read that as 10%, 20%, 30%, 40%, 50%, 60, 70, 80, 90, and 100. And let's call this side component B. So do that in a slightly different color. B. And the same thing happens this way. Where that was 90, 80, we're at 70, 60, 50. Just keep on going like this, and that should be 30, 20, 10, and then you finally have your last line right here at 0. Now let's go to component C. Component C. Let's do black. C. And again, that's right here, that's 100% C. Then we keep going, that's 80%, 70%, 60% C, and just keep on going. So now that we have our lines drawn, some little bit, what is, if we have some component, or we have a combination of something and it's right there, what is its percent of A, percent of B, and percent of C? Well, for its percent of A, we have 100% here. So then we have 90, 80, 70, 60. So that's 60% A. So we have 60% A. And then this diagram, we go this way, so we have 100, 90, 80, 70, 60, 50, 40, 30, 20. Could have just gone from 0, 10, 20. So we have 20%, 20% B. And finally we have 100, 90, or actually we'll start from the other side. We have 0, 10, 20, and 20%, 20% C. Of course, we could have just assumed since 60% of it was A and 20% of it was B, then of course the last had to be 20% C. And that's how you can find the percent of a 3-component system, percent wise. Let's say you also have mixed it with so let's say you have this system mix up, maybe you have 100 kilograms here. Let's say you add 200 kilograms of maybe a system that is 50% B and 50% C. So we find that on our diagram, and that is right here. So do that in a slightly different color. So, and then what we'll do is we'll actually draw these lines together. And we said we added 200 kilograms. So now we actually have a system that is made up of 300 kilograms. But 200 kilograms are from this new system. So the system is mostly going to be closer to this point than it will be to our original system. So it will actually be 2/3 closer. So that's so it'll actually be right there, where this is 1/3 and this is 2/3, and this is 1/3, and this 1/3 represents the original amount of the whatever, if we called this mixture 1, mix 1, and this was mix 2. Erase all that, hopefully. Alright, so now let's say you have there's a phase in here. So when you have, we'll have A, B, C, when you're inside this area, you have two phases. And what that phase is based off of, there's these lines that go across like this. I think they are called tie lines because they tie the 2 points together. So let's pretend you have a system that is made up of 40% A, 40% A, and 40% A. So actually I said 40%. So let's say right there, and 30% B, and also I guess that would also be 30% C, which is 30% C. That has two phases. It has a phase over here, which is mostly B and very little C, and a phase over here that is mostly C and A and very little B. So what is the actual composition of this phase? That phase is approximately 52% A, or sorry, 52% B is 52% B, and I guess I didn't draw that out. That was 2% B, and it was, that's A, so that's 35%, or 35% A. So then the last part has to be 10. I have 10. So what's that total? That's, so it's probably around like 13% C for this one phase, but we actually have two phases, and then you do the exact same thing, and then you use the inverse of the rule for this distance, which represents